So just give me 2 minutes, ma'am, then we start the session.
Sure, sure.
So good afternoon once again to all of you in this teachers training program. Our next speaker is Dr. Shrutidhara Sarma. She is assistant professor in IIT Jodhpur, and her topic of presentation is thin film nano composite temperature sensor and flexible sensors. So before going to start the session, I would like to read her profile. Dr. Shrutidhara Sarma is an assistant professor at Indian Institute of Technology, Jodhpur, in the Department of Mechanical Engineering. Prior to joining IIT Jodhpur, she served in NIT Delhi as an assistant professor of mechanical engineering for a year. She completed her PhD in 2017 from IIT Guwahati and Aristotle University of Thessaloniki, Greece, and thereafter remained a postdoctorate fellow in Kunsan National University of South Korea. She won the prestigious Erasmus Mundus Fellowship from European Commission during her PhD and represented India in Japan through the Genesis 2.0 program. She was also awarded the gold medal for securing the first position in mechanical engineering during her BTech from Tezpur University. Her research interests lie at the intersection of the mechanical engineering, material science, and nanotechnology. Her works in the field of thin film, nanocomposites material, and sensors have been published in reputed peer-reviewed international journals, including ASME Journal of Engineering and Material, the Journal of Cleaner Production, Energies, etc., and international conferences in the country and the abroad. She has guided 2 UG and 3 PG students till now. Besides academic, she is an excellent performer of music. She is a national level table tennis player and a graded artist of All India Radio and a state level player of Taekwondo game. So with this introduction, I would like to request our expert, ma'am, kindly proceed for the session.
Thank you very much, Dr. Sahu, for the introduction. Here is a little bit of change that my topic for presentation is not on thin film sensors today, but I'll be mostly talking about machine learning in thermal and fluid engineering. But okay. I think that's all right, which is because in context to the FDP that we are organizing, I think it's mostly related to AI and ML. So I thought I'll just stick to that. So thank you once again, and I'll share my screen. Okay. If you do not see my screen, or if something disruptive happens, please let me know.
Sure, sure.
Okay. Well, so my name is Shrutidhara Sarma, and I am working currently in IIT Jodhpur, as mentioned by Dr. Sahu. And I'll be talking about machine learning in the engineering, mostly in mechanical, but especially in thermal and fluid engineering. So thermal and fluid, as you understand, thermal means related to heat, and fluid means related to flow systems. So my objective for today's presentation would be to incite a feeling in you so that you understand how machine learning can be imbibed into mechanical engineering domain. There are so many problems, optimization problems, and problems that we encounter in everyday life, because fluid mechanics and fluid and thermal engineering is essentially everywhere. So let's begin. So this would be the outline of my talk. We'll be talking about what machine learning is, then why is it important, and where exactly it can be used, and are the physical models obsolete, and then we will talk about simple results that we carried out in our lab, and we tried to figure out the first and the very initial step of imbibing machine learning into thermal or fluid engineering. So here, I'd like to show you, this is the famous picture of Mona Lisa drawn by Leonardo da Vinci, which we have always seen as a still picture. But now in this small video or GIF, you see that Mona Lisa is talking. You can see her lips are moving, eyes rotating, her facial angles are changing. How this has come is actually through machine learning only. So when we say about machine learning in this 21st century, it is a huge domain and it is integral to everyday part of life. So there have been huge advances in artificial intelligence, in machine learning, especially in our field of image sciences. So this is what is known as image science. And through machine learning, it has offered us so much that we are able to achieve unimaginable tasks, daunting task, which we thought would not be possible a few years back. We never thought a still image could start talking, right? But now we can see that is happening. All this comes from machine learning only. What machine learning does is, it is actually a system which learns from data, and then it predicts or gives a performance based on a program which it itself creates. What I mean by that, I'll come to that in a little bit more detail in the subsequent slides. But when we talk about fluid engineering or fluid mechanics, we can see that it involves huge amount of data in the form of simulations and experiments. So our focus is to see how machine learning can dig into thermofluid engineering and allow us to achieve something like we have achieved in image sciences, just like you can see here in this picture. So what machine learning is, you can usually define it as the science of programming computers so that they can learn from data. So you have a huge chunk of data, which includes both the inputs and outputs, and you have a computer, just like you and I learn from experiences, because a baby doesn't know how to walk, he doesn't know how to talk, but he listens first. His brain understands that other people are trying to say something, and this is how other people are walking. So it looks at those experiences, it gains that experience, and slowly it learns, and finally it is able to talk and it's able to communicate. Exactly that same way, machine learning is where the machine itself learns from the data. Instead of telling the machine that this is what you have to do, you are actually telling the machine that if this is the input, this is what the output should look like. And then you train the machine with several amounts of input and output data until and unless the machine learns to predict itself based on its experience. In 1959, Arthur Samuel, a computer scientist who pioneered the study of artificial intelligence, he described machine learning as the field of study that gives computers the ability to learn without being explicitly programmed. So what I mean by explicitly programmed is, I'll come to that in a bit detail in my subsequent slides, but without being explicitly programmed means you are not telling the machine exactly how to do it. For example, if you are asking your machine to differentiate between cats and dogs, what you will do is you will give inputs of hundreds of images of cats to your machine and another hundreds of images of dogs to your machine, and you do not tell the machine how it can differentiate. The machine immediately by itself will create a program and learn, so that once you show a different picture of a different cat, the machine is usually able to tell you that it is a cat based on the experience that it has gone from all the 100 images that you have fed into that. So here is a small pictorial view. This is an ordinary system, and you imbibe it with artificial intelligence, then it becomes machine learning, which usually learns and can predict. And in fact, depending on the feedback loop, it can also improve its performance. So it can get better and better in predicting, and the accuracy can increase depending on its learning capability and its experience. So another famous scientist, Alan Turing, I'm sure you all of majority of people already know about him. In his seminal paper of 1950, introduced a benchmark standard for demonstrating machine intelligence. He mentioned that a machine has to be at least as intelligent as a human being is, so that you cannot differentiate it from a human being. So machine learning is the application of artificial intelligence where the computer learns from the past experiences, like I mentioned, from the input data, and then it makes future predictions. So Alan Turing mentioned that the performance should be at least of human level. But when we talk about human level, we have a far long way to go, because we are still at the very beginning, and human perception is a very complex thing, and achieving it exactly through machine learning would take obviously a lot of time. Now, that brings us to the difference between traditional modeling versus machine learning. So in traditional learning, what happens is you manually have to create a program. There is a programmer who will use the logic and create a program, and it will give it as input to the computer. So your computer receives the program and the data as the input, and based on that programming logic the programmer has fed, it will give you the output. Whereas in machine learning, what you do is you do not give the program, you do not give any logic, you just give the input data and the output data and let the computer figure out how the input is related to the output. So traditional programming is a manual process, meaning that the programmer will create the program, whereas machine learning is, it has its own rule, which is also, means the algorithm automatically formulates the rule from the data. So unlike traditional programming, it is an automated process, and therefore it can increase the value of embedded analytics in many areas, including data preparation, language interfaces, outlier detection. If there are outliers in a data set, that it can also be figured out through machine learning, and significance detection, like if you have several different variables in a program, in a algorithm, then you can figure out which of the variables are having the highest amount of significance in determining the output. All of these features help us get newer insights, which is not possible in traditional programming, because you are already restricting the program with your own logic. But in machine learning, you can always get something breakthrough, because you are not imposing your logic into it, and you are that's why you are reducing the decision bias. So for example, I can give you that if you are in a restaurant, and suppose you are a restaurant owner, and you are trying to figure out how many customers are going to churn at the end of the day. Churn means people who do not renew their subscription or cancel their subscription. So suppose you have a restaurant and you have 100 customers, and all of those 100 are having subscription to your restaurant. And what you can do is you can feed your computer with the customer demographics, depending on their age, depending on their financial status, and maybe depending on their locality, how far they're living from the restaurant, and maybe how frequently they visit the restaurant, and how many family members they have. And based on all of this, you can input the customer demographic and their transaction as the input data to the computer, and you can give it a historical customer churn rate, that like for the past 5 years, this many customers have churned out at the end of year 1 or year 2, like that. And your computer will essentially learn that program, and if a new customer comes in, you just put that as a data into the computer, it will immediately predict for you whether that customer is going to churn or not. So those kinds of models are known as predictive models, which are very commonly used in machine learning. And this is just an example of a real real day-to-day example, so that you can relate more, but we can obviously have different other examples in case of engineering. Now, when do we use machine learning? So it's a very basic question, and of course we use machine learning. There are a lot of this is a huge field, so we have numerous possibilities where we can use ML. So ML is used when human expertise does not exist. For example, navigating through Mars. So when we say Mars or any other planet or any other planet or any other, let's say solar, even outside Earth, certain things regarding which we do not have data. So we do not have any data regarding the terrain of Mars, how the climate is there, whether it's harsh or not, and in anything related to the terrain. So if you want to send a drone or if you want to send a rover to Mars, what you have to do is you essentially have to feed that computer with lots and lots of navigating data from Earth, because that is what we have. So we have data regarding Earth and a little bit of data regarding the terrain of Moon. So all you will do is you will train your machine with the data of Earth's terrain and Moon's terrain, and you can only hope that it will be able to predict by itself how to take the next step and will be able to successfully navigate on Mars. So this is where the first example where human expertise does not exist, ML can be used. The second is where humans cannot explain their expertise. For example, speech recognition. Now, let's take the example of your family. Suppose when you talk to your mother, you know that your mother's voice, you are very familiar with it. So no matter whether she calls you from, even if she calls you from a different phone number, or if she calls you from a different city, or from wherever, from her friend's phone call, it doesn't take a second for you to recognize that it is your mother speaking. But if I ask you to explain how exactly you are able to know that it is your mother, so it's basically a frequency coming in through your phone, which is getting into your ears, and then the brain picks up the signal, and the brain is finally going through a very complex system before telling you that it is the mother speaking. So speech recognition, if you want to replicate it through machine, then it is going to be, and if you want to use logic in that, it is going to be very, very difficult because it's a very complex process. Similarly, our vision. When you look at a cat, you immediately know, you don't have to wait and think whether it's a cat or not. You can immediately figure out that it's a cat. How do you know that? From your experience. We are a very complex system. We have different simultaneously things going on. The moment you look at something, you get the vision. It goes through your eyes, falls in your retina, go to your brain. The brain sends the signal, and you know that it is a cat. But if I ask you to explain how to do it, you may not be able to do it very nicely. So this is what we call as something natural. So we naturally know that it is my mom. I naturally know that this is a cat. So that is what we are trying to imbibe here. We are just trying to tell the machine that if this is what happens, it is a cat, and this is how it looks like, it's a dog. So, and we let the machine learn itself so that it can predict whether this is a cat or a dog. And the third case is when you have to customize something. For example, personalized medicines. Let's say in case of cancer. So cancer, as you all know, hits everyone differently. So the type of cancer that varies from people to person, and so is the curing procedure. So even if you go for chemotherapy, it has to be completely personalized. So in such cases also, machine learning can play a big role, where you can actually customize the medicine based on patients if you feed hundreds of patients' data to your machine already. And finally, it finds very high importance in handling humongous amounts of data, like in genomics, when you have to study DNAs and alter them, or maybe do lots of permutation and combination. Also, for example, in fluid mechanics type of simulations, which creates a huge volume of data. In such cases also, machine learning is very, very apt. Now, engineering definition of machine learning can be thought about something like this. So you have a task T, which is to be performed by your machine, and you have some performance measure criteria P. So you will measure how good or bad your machine is performing, and you have something known as experience E. So the machine basically learns from experience E, and then performs the task T, and based on its performance measure P, it will improve itself by learning more from experience E. So if I give an example of fluid engineering, so our task could be to predict the fluid flow. Suppose we are predicting a fluid flow around a cylinder. So whether it is a turbulent flow, or it's a laminar flow, or it's a potential flow or rotational flow, all of this, if you want to predict it. So if that is our task, we measure the performance measured by the error between the predicted and the observed fluid flow. So suppose we are carrying that experiment practically in our lab, and then we are predicting it using a computer. So our performance measure would be how different it is from the laboratory results. And based on how we will do that, the experience would be a sequence of flow data and the factors that would affect. So we will create a sequence of flow data. So we will use different Reynolds number. We will use fluids of different viscosity or different density, and maybe the velocity of the fluid we will change, and then we'll let it pass through that cylinder, and then we'll have hundreds of data sets. All those data sets will be giving us input to the machine, and let the machine predict when we give a new flow. So when the machine has been trained nicely, it will be able to predict quickly whether the flow is turbulent or laminar or any other features that it has. So another example that I can give you from thermal engineering is, it would be an optimization example. Suppose you have a sensor which predicts heat flux from temperature, and so the task here will be to optimize the sensor property. Suppose we are building a new sensor and we're constantly trying to improve its thermal and physical properties, let's say thermal conductivity. So how do we do that? We will have our experiences E. How the experiences will be what? We will subject a sensor to different types of heat loads, and we will study its behavior under different heat loads. So the heat loads, maybe you can vary the intensity of the heat, maybe you can vary the type, like ramp or step or impulsive, or maybe you can vary the time frame, how long it is going to hit the sensor, and then you can take out the output data. So basically, when you apply heat to the sensor, it will give you some temperature history, and from the temperature history, you are going to get a heat flux. So your input is your heat input, and your output is your, let's suppose, the heat flux. So what you can do is you can just simply give this input output data as experience to your machine, and then you can do this performance measure by observing what is the difference between the predicted heat flux and the observed heat flux. And then based on that, your machine can improve itself and learn, and it can tell you and optimize that, okay, the sensor gives the best output, let's say in terms of response times or in terms of sensitivity, and these are the sensor properties which will give you the optimized output. So this is how ML can be embedded in thermal engineering as well. This is the typical data science workflow. So when you are handling large data samples, this is what you do. First step is, of course, the data collection. Here you don't care about what kind of features it has, what kind of patterns it has. Your only thing is to collect as many data as possible, because ML needs a lot of data, because in order to train someone, you have to give a lot of inputs. So we need a lot of data. The second step is to prepare that data so that you do some kind of cleaning. If you have some unnecessary data, you get rid of that. If you have some outliers, you get rid of that, and you plot them maybe in an Excel sheet nicely in X and Y columns and rows, so that you know if there are any features, so that you can figure out if there are any patterns or features that exist in the data. In the third step, what you do is exploratory data analysis, where you look through whether there are some distinctive patterns or features which are in the data, whether it has some clusters, so that if required, you can do your clustering, and finally figure out if there are any outliers or if there are any variables which are closely related to each other. Because if the variables are, let's suppose there are two variables which are correlated to each other by 0.99, so that means they are almost equivalent, and they will be almost having the same influence at the output. So in that case, what you can do is you can get rid of one of the variables, and losing one of the variables and getting rid of one of the variables will significantly lower down the dimensionality of your problem. So that comes under exploratory data analysis. The fourth step is then the machine learning. Once you have set up your data, once you have done everything, you train your machine. Now you give input to your machine, and you let it run and learn itself. And the fifth one is your visualization, which is essentially summarizing and interpreting the information that you have received so far. So visualization can be in forms of graphs and plots. It could be in forms of classification and detection, optimization, or anything like that. So this is a typical data science workflow which is used, and machine learning is a part which comes only at the fourth step. Now, when we talk about machine learning, there are generally three types. The first is called supervised, the second one is unsupervised, and the third one is called reinforcement learning. In supervised learning, just like supervising PhDs, it is done under human supervision, and the machine learns from examples which are having labels or targets. So you put different labels to your input data, or you put targets to your input data, and the machine learns from those labels, and then it predicts something. In unsupervised, the machine learns from unlabeled data. So you just give a lot of data to the machine, but you do not put any label, and let the machine learn itself. In reinforcement learning, it is mostly goal oriented. So reinforcement means it will try different paths, and it will see which of this path is more rewarding to it. So it will select the path which is more rewarding to it, and that reinforces its selection. So suppose if there are 4 paths A, B, C, D, and the machine sees that if I go follow path B, then I'm having the best result, then that path gets reinforced. So next time when it has to go, it will not go by A, C, and D. It will definitely choose B. I'll come to that in a bit. So this is how reinforcement learning takes place. And last but not the least, if you talk about how the machine learns, then there could be another 2 ways of learning. One is online, that means in a line. So you can feed data one by one to the machine, or it could be batch learning. In batch learning, it is not possible. There are certain problems where it is not possible to feed data one by one. Instead, you will take a whole chunk of data, you'll take the whole batch, and then let the machine learn. So this is why it is also known as offline learning. So supervised learning, like I mentioned, it learns from labeled data. This is the best example that you can see. The general example of a cat. So if you want your machine to detect whether it's a cat, what you do is you give different labels like ears, nose, tails, paws, and then you tell the machine that if these are the features which are available, then it is a cat. Otherwise, it is not. Just a simple example. So the machine will, and then you feed with hundreds of, let's say, images of cats. So the machine will then learn from its labels, and then it will give you the known output, cat. So if you give a new image of a cat, it will look for these labeled features. If those features are available, it will tell you that it is a cat. Similarly, you can take an example of engineering. Suppose if you want to detect a type of flow, and let's say based on Reynolds number, we know that for a flow to be turbulent, it has to cross a certain Reynolds number. But let's suppose we are not telling that to the machine. We're just telling it that these are the parameters: density, velocity, diameter, and dynamic viscosity, and this is how they vary. And if they vary, then this is the output. If they vary like this, we get laminar. If they vary like this, we get a turbulent flow. So like that, you can train the machine, and the machine by itself can predict what type of flow it is. Now, when we talk about supervised learning, there are 2 categories. One is called your classification, and the other one is called your regression. But you must also understand that supervised learning is very, very labor intensive data, and you are actually blocking the insights because you are already giving biased decision. You are already telling you are already imparting your logic onto the computer so that it is not able to predict on its own, which is actually the pros of unsupervised learning. Because in unsupervised learning, you are not imposing your decisions onto the computer. So in a way, unsupervised learning is better than supervised, but it will take much longer time. We'll come to that. In supervised algorithms, now as I was telling, there are primarily two categories. The first one is classification, where you classify something, like put it in a box, whether it's a cat, whether it's a dog, or something else. And the other one is regression, means quantitative. So if you want to figure out a number or something like that. So the basic difference is that in categorical or classification, the machine will learn to predict discrete values. So it will, if it is a discrete value, so it will be able to classify as a different category, as a class or a label. For example, if you see an article in a newspaper and you want to figure out whether this article belongs to economics section, or political section or laser section, that will come under this categorical supervised algorithm. On the other hand, regression analysis is involved with problems where you would like to predict, let's say, the sales of a vehicle based on a given set of parameters like mileage, age, brand, etc., or predicting the salary of a job based on its description. So these are the two types, major types, which comes under supervised learning or machine learning. And the basic model formulation for supervised learning you can understand is through this linear equation example. So in its simplest form, we can write y equal to fx plus epsilon, which is analogous to y equal to mx plus c. So x is the input variables. So x inputs can be from x1 to xn or xp. And we know that there is a relationship between x and y. But how is that relationship happening is for us to figure out. So for that, we have to figure out f. F means the function which relates x with respect to y. Now, while relating that, you will see we also add a term epsilon, which is known as the bias term. This bias term actually helps us to flip values. What I mean is, for example, if you talk about the curve y equal to mx plus c, you see if there is no c, if it is simply y equal to mx, then your curve will always pass through the origin. Your straight line will always pass through the origin. But the moment you add an intercept value c, you can now make the curve go up or down or move left or right. So that flexibility comes from this biased error, random error term, which is why we add epsilon. Now from here, we are supposed to figure out what is f, how x is related to y. Now, if it is a quantitative variable, if it is a number, then we call it a regression. And if it is a qualitative variable like category or class, we call it a classification. These are the two types of basic supervised learning that we were talking through. However, in here, there is also another problem, because not everything would come under the regression or classification. What I mean is, in case of a logistic regression, what you do is your output comes in terms of binary. So suppose if you are trying to figure out a quantitative variable, but your output is binary, it's either 0 or 1, nothing in between, no fuzzy. If it is just binary, then you can simply treat it as a category as well. What I mean is, suppose you are doing a mathematical optimization and you are expecting values which output is only in the form either 0 or 1. So you can take it as a quantitative output, or you can take it as a categorical output as well, because I can simply put 0 equivalent to cat and 1 equivalent to dog. In that case, it becomes a category. So there is a slight bit of gray area here, but otherwise, in most of the cases, we are good enough to go with regression and classification. Now, why do we want to estimate f? So our basic thing why we want to estimate f is two reasons. One is prediction, the other one is inference. Prediction is, what if we have a new x, would we be able to figure out y? In case of inference, we are trying to figure out what is the relationship between x and y, how they are related. So it will depend on our motivation, which will influence us the approach we take to model f. So in certain problems, you care only about the prediction accuracy. If you want to predict flood, you don't worry how the input and output are related to each other. You don't worry about it. You just worry about the prediction accuracy, that I want to predict with 99% accuracy that flood is going to happen or not, depending on various things like the size of basin or the climate of that, the rainfall, and all of these things. And in other cases, you do not care about the accuracy of prediction. You only care about the model interpretability. So model interpretability is another challenging task in machine learning. A lot of research is going on in there. In model interpretability, no matter how easy the problem is, it's very difficult to actually figure out which exactly are the variables and how much they're influencing the output. So there is a trade-off that you have to choose between the two when you go for estimating or predicting or optimizing or solving any kind of problem using machine learning. Now, like I mentioned, in unsupervised learning, we have what we do is we give unclassified and unlabeled data to the system, and the system itself uncover some patterns from the data. For example, here the system itself sees that there are 3 clusters, and it gives different colors depending on whatever it learns from the unlabeled data. So the thing is, if the data is unlabeled, so we can have disruptive insights, we can have breakthroughs, we can have insights that we never knew, which was not possible in case of supervised learning, because we are already labeling the data with our own logic and we were not letting the machine to figure out itself. The only thing is, in case of unsupervised learning, it will require much more experience compared to supervised, because we will need a lot more data, and a lot more data means you'll have to handle a lot more dimensions, and also the accuracy can be quite less compared to supervised learning. And thirdly, I was talking about reinforcement learning. In reinforcement learning, I was talking about it reinforces the path which gives is the best output. So you can, the best example I can give from for a reinforcement learning is maybe a game. So if there is a game and there are different paths, and when you move through different paths, you gain number of points. So your machine, what will do is, it will figure out the best possible way, the fastest way in which it can maximize its points, and so that it can earn more and it can earn fast. And that can happen only when its moves are reinforced. So it will first check that if I go through this path, I get the maximum point. So this path is now reinforced. So next time he will take that path only before moving to the next stage, like that. Similarly, you can take the example of GPS and using traffic signals. So if using machine learning, you can figure out that this particular zone can have this amount of traffic on a working day, and this needs to be avoided if I want to reach in a particular destination in my fastest possible way. So this is how reinforcement learning happens, and the main goal is to determine the ideal behavior within a specific context in order to maximize its performance. Now, this brings us to artificial neural networks, and artificial neural networks are these are the actually basis of machine learning. How machine learning is happening, it is through artificial neural networks, and ANN is something which you can think of analogous to our human brains. So we have a lot of neurons here which releases synapses, and through which we understand, we take information, we learn, we predict, we do a lot of things. So ANN are just like our neurons, they're massively parallel and distributed system made up of simple processing units, which are also known as neurons. And then based on their synaptic connection strength, they will store the data, and then the knowledge acquired by the network from its environment will be used in the learning process. And depending on how complex the network is, what amount of data you are feeding into it, it will learn, and then it will help you in predicting solutions to your problems. So some of the most interesting properties of ANNs are it can learn from examples irrespective of whether it is labeled or unlabeled. So it can go for both supervised or unsupervised learning. Secondly, it is adaptive to change. So you can change your connection strength to make the machine learn better. By connection strength, I mean all of the neurons have a certain weight attached to it, which will ultimately determine which neuron is having the highest significance in your output. So you can change the weights attached to the neurons, and you can check whether which of the combination is giving you the best output. So your ANN is quite adaptive to change, and changing the weights does not really affect the performance of the ANN. I mean, it does not stop working. Only thing, it can get better, it can learn better. Third thing is linearity. It is not highly non-linear, so you can attach one neuron to several others, and that's why, although the complexity increases, the learning is also very fast, and the prediction is very, very accurate. And finally, the most important is your fault tolerance. And fault tolerance means even if one of your neurons or one of your connection is damaged, the whole network will not stop working, it will still continue to work without that particular neuron in being there. So it's just a better alternative than the classical solutions for the problems that are characterized by high dimensionality, because we don't have to apply our logic, we don't have to write long pages of codes. So it can help us reduce noises from experimental data. Experimental data always has lots of noise. We can use ANN to get rid of those unwanted, unnecessary data, and so we can have we can get rid of imprecise or imperfect or data or outliers. So we can have much more fidelity in the data we have, and then we can clearly find solution to problems, including the fluid flow problems or the thermal problems. Now, this is how a typical artificial neural network model looks like. Here, I would not go deeper into it. I would like to explain, but I think we have time constraints, so I simply try to tell you in a very concise manner. This x1, x2, x3 up to xn, these are your inputs. These are the various inputs that you know for a particular problem, and you are simply giving it to your computer. These are called passive nodes because they do not have any action to play in altering the signal or anything. Next comes the neurons. So these are the synaptic weights which are attached to the neurons. So WI1 means it is a weight attached to input 1, weight attached to input 2, like that. That means whatever x1 you have, this will get multiplied by the weight WI1, and that will go until here. So like that, if from every input multiplied by the synaptic weights, it will come as a whole, it will come here. So here what we'll do is you will sum it up all. So this is a summation function. And then because we wanted the flexibility, remember I mentioned how I said that adding a bias can help you move up and down. So because of that, we add a bias. So the main function of this bias is to provide every node with a trainable constant value. So it allows you to shift the activation function to the left or right. We'll come to the activation function next, but just understand that adding a bias is very, very important for successful learning. So it is like the constant term, like I mentioned, it is y equal to mx plus c. So because we have the c, we can move the graph up and down or left and right to fit the data in a much better way. So similarly, we have a bias here so that our neurons can learn more successfully. Then all of this goes into this activation function, which is essentially the function which will convert to the output. So when I say about output, suppose you want output with values which will lie only from -1 to +1. So then you can give a sigmoid function with the lowest and the highest value as -1 and +1. And what you will do is, no matter what comes here, no matter what value comes here, your activation function will essentially convert it to fit into that domain of -1 to +1. And that will be shown to you in terms of output. So this value passes through the activation function, and that is finally given to the user in terms of output. So mathematically, it looks something like this. This is the addition of all the weights multiplied by the inputs and plus the bias, which is essentially a function of the output that you are going to get. So like I mentioned, the bias can be incorporated as, you can think of the bias actually as another weight which is clamped to a fixed input. So it is just that you do all the maths, you do all the summation and just add the bias. So you can think of it just as another weight which is clamped so that we can fit better. And these are extra free variables, so they make the neuron much more powerful, so they are more successful in learning. Now these are the activation function, like I mentioned, which are also known as squashing functions. So it limits the amplitude of your output of the neuron. So basically, after going through all this summation, this or whatever you get here, it will pass through this activation function, which will essentially limit the amplitude of your output. So for example, if you want a linear output, so then you can define it as linear, a f of n is equal to n, and then you will gain a pure linear output like this. Suppose if you want to keep a threshold value, that you want to cancel some noise, and you say that I will allow the signal to pass only if this threshold value is crossed, then you can also put that, and anything below that threshold value will be eliminated and will not be considered. And finally, sigmoid function, which is one of the most common function. So sigmoid something like this. You can use log sigmoid or hyperbolic tan sigmoid. That means you are limiting your output and upper bound and lower bound. Let's say if you want to keep your values only between +1 and -1, you can do that using this log sigmoid or tan sigmoid function. So there are a lot more other membership functions and other activation functions which helps us frame our output in a way that it is easy for us to understand. Then comes this multi-layer feed-forward networks. There are many different types of artificial neural networks. There are 8-built functions in MATLAB. If you want, you can also go and check. So the best example is, remember I talk about reinforcing. So feed-forward network is what basically, depending on the output, it will give you a feedback, and depending on the feedback, the machine will improve itself. So how that happens is, suppose this is your input layer. You're giving inputs here, which goes into hidden layers. All of these things happens within the hidden layer. Addition of weights and connecting one neuron to all other neurons, then summing them all up, then passing through activation function. All of these things happens there. And finally, it is given to the output. So now once the output is given, the neuron itself will understand whether it is close to the, this is what is known as training. So in training, you already know the input layer and you already know the output layer. So you allow the network to learn itself and check whether it is getting the output what it should get. So let's suppose I'm telling you that your input layer is like 1, 2, 3, 4, and your output is 10, 20, 30, 40. You do not tell the neural network how it is going to get 10 from 1. You just simply feed the inputs 1, 2, 3, 4 and the outputs 10, 20, 30, 40. The network will itself learn and then it will try to predict the output. Okay. So let's suppose first time it predicts 9 here. Instead of 10, it predicts 9. Immediately a feedback will be given to the network that it should be 10, not 9. So you have a difference of 1. So the network will improve itself. This hidden layer, within this hidden layer, it will improve itself and it will predict again. Let's suppose next time it predicts 9.5. Another feedback will be given saying that now there is a difference of 0.5. It should be 10, but you are giving 9.5. That way, the network will learn over and over and over again unless it is able to predict 10. So once it predicts 10, 20, 30, 40 here, we know that it has been trained. Now, if you give another number, let's say if you give 5 to this system, the system will automatically predict 50 for you. It doesn't matter how it is relating the input to the output. All that matters is if you have enough training data and if you have enough number of hidden layers, then you have a very good feedback system, then your system is able to understand very quickly and predict for values which are not known. Now, this input layer are known as passive layers because they do not really play any role in signal modification. So they are known as passive nodes. And their job is just to transmit the signal to the next following layer. And hidden layer here, although I have shown as 1, there could be multiple hidden layers and there could be numerous nodes in one single hidden layer. What I mean is, one hidden layer can have 10 different nodes and there could be 10 different hidden layers like that. So the hidden layers have arbitrary number of layers and arbitrary number of neurons. All of these neurons may or may not be connected to each other. So you can imagine this is a very complex process. Here only there are just 2 neurons and these are connected to all the 4 inputs, so it looks clumsy. Imagine if I add 10 more neurons and all of those 10 neurons are connected to each of these nodes and each of these output, then how clumsy it will look like. So it's a very complicated process, just like our brain, but it can predict very nicely. So these hidden layers, these nodes are known as active nodes because they participate in signal modulation like this, like I already mentioned. All of these things goes inside the hidden layer, and it would have been nice to give you a better example, but I don't have time for that anyway. And then finally, all these hidden layers finally give you the output layers. These output layer are the neurons, which corresponds to the number of output values of the neural network. And these are also active nodes because this will give you the ultimate output. So you can by yourself decide what are your inputs and what are your outputs, and then you can use such layers to predict values for you. This is what we have actually done in our lab. I'll show you quickly in a couple of minutes how we did that. Now, the most common types of ANN applications in mechanical engineering that I can think about is classification. So where it can predict different class of inputs, like the types of flows. Then optimization, of course, if you want to optimize, let's suppose if you're trying to build an aerofoil where you want to minimize your drag and maximize your lift, that kind of optimization can happen through ANN. Then function approximation, like time series modeling, where you are trying to figure out the relationships between input and the output. And finally, data mining, when you have a huge amount of data and you're trying to extract knowledge out of that. The best example would be of turbulent flow, because we have lots of data of turbulent flow, but we still don't know anything about it. We are still not able to predict or model turbulent flows nicely. So data mining is one of the biggest, I think, platform to use ANN or ML in fluid engineering. Now, when coming to practical application of ML in fluid engineering, here is a picture by Vincent van Gogh. This is a painting which has been now converted to, again, a video using machine learning. You can see all of this are the fluid flows. So I don't know whether this existed in real or it was the imagination of Mr. Gogh while painting this. But this is how you can see patterns in every fluid engineering problem, whether this is just a simple example of a painting, but this is how what I want to tell you is that fluid mechanics is absolutely everywhere. They play a central role in every big industries, including health, defense, transportation. So controlling fluid flows, figuring out where to put the sensors in order to measure them, then reduce the complexity of modeling. And these are very important tasks in upcoming challenges of the modern upcoming fluid industry in the next century. So, and most of the fluid mechanics problems can be written as optimization problems. So, which itself are very, very challenging because they, number one, because they include a lot of data. Number two, they are highly nonlinear. And third, they are highly dimensional. Highly dimensional means even if you have to model the fluid flow around a submarine or a jumbo jet, you will need maybe a billion degrees of freedom of the fluid. So to simulate such a flow in lab is still not, in a computer is still not possible because our computers are not even powerful enough to handle that. Besides, they use nonlinear equations like the partial differential equations, like the Navier-Stokes equation. So you can use evolutionary algorithms, genetic algorithm to design and optimize a better flow system. But these are the challenges that are upcoming with your fluid mechanics. So like I mentioned, controlling fluid and locating the sensors and model reduction are the most challenging problems that we are going to have in fluid mechanics domain. So whether you are trying to create a flow simulation around a aircraft or you are trying to simulate the flow around a submarine, the number of degrees of freedom required will be really, really high. The dimensionality goes up like very high. So which is why we what we do is we stick to machine learning, which doesn't actually need to know how it works. It can just predict how things, this kind of flow fields can happen. So when I talk about evolutionary algorithm, there also ANN has to play a big role. So combining this ANN and machine learning, we can design and develop ways to control fluid flow. And once we know how to control fluid flow, there again we have a long way to go. Because, for example, this is an example of multi-panel plate where you can actually change the angles. You can change these angles in order to control the lift and drag. This experiment was done by Richenberg in 1960s, and you can essentially change the angles to find the optimal configuration where you will be having the maximum lift and minimum drag. And when you plot it in, and you can see that after a series of iteration, we reach here where we'll have the minimum drag. But now with the help of machine learning, we can do it really quickly. The second example is of a ball, this is a game actually, where the ball falls from the top and it lands somewhere in one of these boxes. So by actually using binomial Gaussian distribution, here you can actually predict which path the ball is going to take and exactly where it is going to land. So here this reinforcement, remembered my example of reinforcement learning, where I said the ball is going to pick up, the machine is going to pick up a way which is going to give it maximum results in the minimum amount of time, and it gets reinforced through feedbacks. So all these things are possible where machine learning can be embedded. And finally, the good thing about fluid mechanics is that patterns exist everywhere, even in the most complicated flows. So here's an example of flow of clouds over Rishiri Island in Japan. When you look at it, it is quite similar and analogous to a simple flow over a cylinder. So this flow of cloud over Rishiri Island are big. They're having very big dominant patterns and coherent structure, but they resemble much simpler flows. So that helps us because we can actually now model and simulate and control quickly and robustly using machine learning. So machine learning is mostly aimed around extracting or characterizing or utilizing low dimensional or dominant patterns like in big data. And you can train your machine using a simpler example like a flow over a cylinder, and you can use that experience to do a task over a very huge amount of data like that. And but most of the experiments regarding fluid mechanics are carried out in laboratories because our PCs are not powerful enough, our computers are not powerful enough to simulate all the degrees of freedom that are essentially required to model a complete three-dimensional flow field. But experimental data, there is only one problem, that in case of experimental data, there will be a lot of noise. And if we can get rid of the noise, then we can have much more fidelity about the flow estimates, which we can essentially do using the artificial neural networks by cutting out the noise. And then here also, we can use our machine learning. And finally, everything in research, I think, is mostly inspired by nature. Here also, it is inspired from biology, where we are trying to understand how biological systems are, how the brains and all our nervous system work so seamlessly to interact with the environment. We don't know how it happens, we just know that it happens. And we are trying to figure out a way so that we can apply such things in our engineering problems to get solution. For example, if you look at the eagle now, it is interacting seamlessly with the complex turbulent flow fields without having the knowledge of any fluid mechanics or without knowing any Navier-Stokes equation. It doesn't even have an idea of the 3D flow field around it. It just learns from its experience, and it manages to fly in an elegant way, which goes much beyond our comprehension and much beyond what we can practically achieve in case of engineering systems. But all of this, if we want to achieve someday, if we want to fly like a bird, if we want to interact with flow fields, just like the eagle is doing, forget about the eagle. We talk about a small insect. The insects are having very simpler nervous systems compared to eagles. But even then, they know what is the optimized way to fly, what is the optimal way they can get the maximum lift and minimum drag, how they can travel faster in a very short span of time. All of this, if we are going to include, then we have a long way to reach there. But whatever I talked today, it represents just the tip of the iceberg, maybe just 1% of what machine learning can actually do for us. And in 6 months' time, maybe you and I will see technologies which we are not even aware of now. So lastly, finally, a small example that we carried out in our laboratory. So we created a sensor, a thermal sensor, and then we collected a lot of data set where we subjected the sensor to a different types of heatings with, let's say, varying the intensity of the heat, like 1 watt, 2 watts, 3 watt, like that. The heating was done by laser. And then we took those signals. The sensor gave us a temperature signal. From those temperature signal, then we analytically formulated the heat flux. So it's a long and tedious procedure from the signal capturing by the sensor, then filtering out the noise, then figuring out the temperature history, and then calculating the heat flux. All of this is a very lengthy procedure. So what we did was we tried to build a smart system which can essentially predict the heat flux from the temperature history without even going through all the mathematical calculations. So what we did was we built a neural network and we trained it with hundreds of data. Like if this is the hit input, this is the hit flux that it generates. If this is the time period, this is the hit flux it generates. Like that, we created a very long training data. We trained our neural network and then we allowed it to predict hit fluxes for hit inputs which are not known, and it was able to do that very nicely. And once it did that, what we tried to do was we tried to correlate the performance of the sensor with respect to its thermal and electrical properties. Those sensors were called thin film sensors, and this is actually a plot which shows you how the thermal electrical properties of the sensors are related with the applied hit input. So our target was to create an ML model that can map the thermal sensor performance with its properties. So right now we have done only with thermal and electrical properties, but it can go way beyond that to the structure of the sensor, to its composition, if you're talking about nanocomposites as the sensing material, or maybe even its size. So all of this can be incorporated. So we are thinking, is it possible? If it is possible, so that what kind of data we will need, and if it is possible, and if we have the required amount of data, will we be able to create sensors which are tailored to user demand? So depending on what application you are looking at, we can build a sensor which can essentially predict the heat flux or the temperature for you just by machine learning. So this is what is mostly my talk is about today. And thank you for having me here. You can always contact me through my email, shrutidhara@iitj.ac.in, or you can also visit my website here. If you have any questions, you can write to me anytime, and I'm free for any discussions related to fluid and thermal engineering, sensor design, or also incorporation of artificial neural networks and machine learning into these fields. So thank you very much. This is the end of my presentation.
Thank you very much, ma'am. Any participants, if you have any query or question, you can ask. Okay, thank you, ma'am. It was a wonderful session. We have learned about machine learning and different concepts in this session. We have learned about the use of machine learning in the mechanical engineering, especially in the fluid mechanics. We also understood about the difference between the traditional modeling and the machine learning, different steps involved in the machine learning process, and the type of machine learning process like supervised machine learning process, unsupervised machine learning process. And we also understood about the artificial neural network activation functions and the most common type of AN applications in the mechanical engineering. So it was a very wonderful session, ma'am.
Thank you.
Thanks to ma'am to give us a time for this session, and definitely in future also we will connect with you.
Sure. I'm open to discussions anytime. Thank you very much, Dr. Sahu. Thank you everyone for attending.
Okay, ma'am. Have a good day, ma'am.
Thank you. May I leave the call now?
Sure, ma'am. Sure.
Okay. Thank you. Thank you once again.
Nitin sir, I must say you are doing a wonderful job. I mean, you
Thank
are handling this complete workshop and you are doing a wonderful job.
Thank you very much, sir. So, dear participants, I have forwarded the feedback link for this session. That was the session number 30. So now you can fill this form. And thanks to everyone to be a part of this event. This was the last session. Tomorrow again we will meet. Tomorrow there will be 5 sessions. I will just give you a brief about the session. Okay, so the first 2 sessions will be delivered by Mr. Shrutidhara NC. He is CEO and Director of AMS India Private Limited. Then we have 2 more sessions by Dr. Dushyant Singh. He is Assistant Professor MNNIT Allahabad. And last session will be delivered by Dr. Sriram K. Vasudevan. He is principal in K. Ramakrishnan College of Technology, Coimbatore. So all the participants, thank you very much to be a part of this event and be with us today. So please join us tomorrow also, and have a nice day to all of you. Thank you.
Hello, sir.
Can you submit
Yes, sir.
link of session, sir?
The feedback link for session number 14 is not yet received.
No, I have forwarded. Okay, no issue. I have forwarded.
For session number 13.
No, session number 13. That was the session number 13. So
That we have already submitted, sir.
13 number session is for the okay received. 14 number session, please say only 14 number.
Okay. Okay, that was the session 14. The last session was session 14. So I have forwarded it in the chat box. You can fill it.